Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we've seen some nice examples of probabilistic programming, and that's great because that means I don't have to explain what probabilistic programming is. But when you write a program, you want to have variables that aren't just numbers. And most machine learning models that we build, the variables are like either real values or Boolean values, or they have one of a set of states, right? That's not very exciting. When I write programs, I want to have variables that are strings or dates or images. And so how can we start to sort of move machine learning out of this sort of numbers zone and into more interesting objects? So what I'm going to talk about today is strings. So here's a piece of code coming out of Microsoft, and the NSA has blacked out some of this code. But luckily you can buy it from us and run it. And so when you run it, it says, "Hello, uncertain world." And my question to you is, what was the blacked out code? So we've got two strings, A and B, and we're concatenating them together with a space and some exclamation marks. And the result is "Hello, uncertain world." Okay, so I'm sure you're all thinking it. You're just so shy that you're not going to shout it out. But yeah, so the first string A could be "hello, uncertain" or "hello." And the second string could be "world" or "uncertain world." So how can we solve this kind of problem using probabilistic programming? So here we have the Csoft probabilistic programming language, which we're working on. And again, this is powered by infer.net. This is a new way of driving infer.net. And so what we say is string A is random. This is the keyword in Csoft that says, create me a random variable given this distribution. And this distribution we're going to give is an improper distribution over all strings. So it just says, it's uniform over all strings. Don't worry about the details. And then the second string, B, is also going to be uniform over all strings. And now we can do stuff with these unknown strings, with these uncertain strings. So we can concatenate them together. And then we can observe the result. So we can say, observe that the result is "hello, uncertain world," and infer back distributions over what those strings were, A and B. So in this case, A gives us 50%, hello, uncertain, hello, and B gives 50% world, uncertain world. And you can download this and try this out. This is not vaporware. This is downloadable code. So let's look at a more interesting example than "hello, uncertain world." So let's talk about a more exciting operator in string space. String format, or actually quite a remarkably complicated operator. What string format does is it takes a string with some placeholders in it. I guess I've got a laser on here somewhere. Can you see that? So it takes a string and it has a placeholder in it, like this, and then it substitutes in some other string for that placeholder. Okay, so let's look at a simple example here. So what I'm going to do is I'm going to say my name, a name, is drawn from the distribution over all capitalized strings. So that's some uncertain capitalized string. So that's a string with an uppercase letter and some lowercase letters after it. And I'm going to use that uncertain string, format it through string format, so put it in where that placeholder is, and observe the result. And the result here is not too surprising. It's 100% John. It's a great result. So let's look at something a little bit more exciting. What if we don't know the template? Okay, so name is still string capitalized, but template now has this more complex prior. So what do we think about when we have a template? Well, typically a template, the placeholder tends to correspond to some words that we were going to put in. And so we'd expect there to be word boundaries at either end. So we can say that the template is some string that obeys this structure. So it's like any string plus a non-word character, plus a placeholder string, plus a non-word character, plus any string. Okay? And obviously you can make more sophisticated versions of this. But now we're going to take that random string and use that as the template in string format. Okay? So now both arguments to string format are uncertain. They're all just strings. So now if I observe the text, my name is John, what will the result be? The result is 100% of inferring template is 100% on my name is placeholder. That's the only string that's consistent with those priors. I cheated a little bit here, right? Because there's two capitalized words in this string. But my prior said that I have to have stuff either side of the name, so that's how I cheated. But supposing I was unlucky, and the string was instead, hello, my name is John. Now there's some ambiguity, right? There's two possible placeholders that could have happened. Hello, my name is blank, or hello, blank name is John. The system doesn't know which of my and John is the actual name. And there's two ways you could get around this problem. One is you could build much more sophisticated models of what a name is. So you could perhaps use a census or something. Two is you could throw more data at the problem. So let's do two. So in two, what we're going to do is just going to throw more data at the problem, and there's no shortage of text, it turns out. So we just create a second piece of text, which are also talking about greetings and names. But the crucial thing is that we'll have a second piece of text, we'll have second name, different piece of text, but the template is now shared. So the same template variable is used in both places. And now if you run inference, the ambiguity goes away. Because whilst the result from the first string is my or John, and the second string is my or Andy, when you put them two together, that means, sorry, I got that the wrong way around. When the template is either hello, my name is blank, or blank name is John, or my name is blank, or blank name is Andy, the common one is my name is blank, which is what we wanted. And you can go further. So in addition to inference with strings, we can start to introduce objects like dates. And now we need to convert dates to strings. And we have to handle uncertainty in that conversion. So here, I'm now going to say, I have some date. It's a date time. That's C#. It has a month and a day and a year and all this kind of stuff. So it's not a string object anymore. And so when I want to convert it to a string, I'm going to have to format that somehow, which is going to involve some format string, which in itself may be uncertain. And so I can take that date, pass in this uncertain string format. So in this case, I've just picked it's one of two formats. So I convert it into a string using one of these formats. And then I've got a slightly more sophisticated template here that I probably won't go into. And then I just now format up that template with two arguments, name and date string. And so now, if I do inference on some text, like Fred was born on 6th of May 1963, then we get back the name, Fred, the date as a date time, the format that it's written in, the string corresponding to that date, and the template. All from that short program. So this is a very powerful framework now that we're sitting in for doing inference over much richer objects than ints and doubles. So the title I gave was Belief Propagation in Strings, so I should talk a little bit about how this works. So in order to work in infer.net, we have to make string distributions and date distributions that look like they would fit into standard inference algorithms like expectation propagation, belief, and belief propagation. So in order to do that, when we're sending out beliefs about strings or dates, we need to have distributions over those things. So what does a distribution over a string look like? It looks like this. An automaton. So I assume most people have come across or are familiar with automata, but I'll just briefly go through them. So an automata has a set of states, a start state, and some of the states are marked as n states, and then the edges are marked with, in this case, distributions over characters. So here the first edge is uniform over lowercase h or uppercase h, and the rest of them are point masses at particular letters. So this is hello with either capitalization. And we can associate, then we can also have loops in our automata. So we can say any number of spaces before hello and any number of spaces after hello. And then we can have alternatives. So we could say hi instead of hello and end here instead. And we have allowed these epsilon edges that say just instantly transition. Do not omit a character. Okay? And this actually defines a distribution over strings. As well as it's normally seen as something that accepts certain strings, but if it's a weighted automata, it defines a distribution over strings. And these have been widely used in speech recognition for a long time. But what we've done is make it so that these are the messages passed inside expectation propagation. And that is actually very useful because it means that you can combine them with all the other types that are in info.net. So you can combine them into your PCA algorithm or your LDA algorithm or whatever it might be and do combined coherent inference across all these data types at once. So no longer when you're faced with text do you have to convert it to a bag of words before you do anything with it. Okay, so a little bit of details. One important thing is that you can determinize weighted finite automata so that things are substantially more efficient. And if you use expectation propagation, then you get this backwards message coming in, this context message, which allows you to massively simplify a lot of the and speed up a lot of the automata operations. And that's a very important trick. So what's good about automata? So they have some nice properties. They're closed under mixture operations, they're closed under product operations, and they're closed under concatenation operations. And these are some essential properties for doing kind of string and sequence operations. And if you want to actually do stuff to them, like string format or substring, all the kind of things that you want to do with strings and sequences, well, you can do that using a finite weighted transducer, which is the form of an automata over multiple sequences. And I'll show you some examples on the next slide. And whilst I've talked a lot about strings, you can actually use this approach for any list of anything. So we've actually been using it for lists of things other than characters. So a string is a list of characters, but if you want to use it for a list of people, or a list of countries, or a list of whatever, then you can use them for that as well. So just to give you some examples of what transducers look like, so the concatenation transducer starts here, and the transducer, you sort of have operations on the edges that map from the various sort of sequences involved. So you copy from sequence 1 to sequence 3 a lot of times, and there's an epsilon edge, and then you copy from sequence 2 to sequence 3 a lot of times, and then you stop. And so that concatenates sequence 1x and sequence 2y to give you sequence 3z. Now what's clever about using transducers is that you automatically have all the belief propagation messages in all directions. So with a transducer, you can start with z and go to x and y, or you can compute the projection of transducers in all these different directions. So by defining the transducer, you're defining you have now the ability to send and compute the belief propagation messages in all directions, which is gets pretty complicated in many cases, as you can imagine. If you have an uncertain format and an uncertain string coming in to be passed and some uncertain arguments, trying to do inference in that situation can get quite hairy, and transducers just sort of normalize it all. I'm not saying there's no issues. The main issue is that they sort of can get, the resulting automata can get very large, and so you use some tricks like projecting them down to simpler automata as part of the EP step. Okay, so just one example before I run out of time. So this is a problem that lots of bioinformaticians have looked at, which is motif finding. So the idea is that in your DNA, there's some motifs that mean something. A motif is a small sequence of bases. And so people have built motif finders. And what I'm going to show you is a motif finder on one slide. Okay, so here's a motif, and what you find is that it's not the same sequence of characters every time, but there's a lot of similarity between the sequences, and you've got to try and discover them. So here is our data. This is synthetic data that I just made up, and I'm sure you can all see there's a motif in each one of these sequences. Everyone spot the motif? You see it? Yeah? You got it? Yeah, it's really quite hard, isn't it? So let's write a program to find the motif in this data. And here it is. So this is the entire program, well, with some boilerplate missing. So we're going to assume some Dirichlet prior has been provided for our motif. So that's just going to say what's the probability distribution over the confidence of the probability distributions over bases at each point in the motif. So I'll just draw from that. That's going to give us our motif probabilities, which defines the motif. And for each of those sequences you saw on the previous slide, we're going to instantiate that motif. So find the exact sequence of base pairs that are going to appear in that sequence by sampling from the motif probability distribution for that character. Then we're going to choose where the motif appears inside that sequence. And now the string stuff comes in. So now we're going to create a left-hand string of background characters. And then we're going to, and at the bottom contain a right-hand string of background characters. And then in the middle we're going to plug in this motif. Okay, so just a simple motif generating process. And then we observe that the sequence is equal to left plus motif plus right. And now we can go back and apply that to our synthetic data. And boom, these are the highest probability positions inferred by that program. And now hopefully you can see the motif in all of these sequences that's been found by the program. They're not identical in every case. And in one case, the highest probability position was not actually the one that was created in the synthetic data set, because actually that one does look more probable. These things happen. And this is the motif that was used, that was inferred back from this data, which is pretty close to the ground truth. Okay, so a motif finder in one slide. So inference over strings enables a wealth of new machine learning applications, particularly when the sequence is involved. So in bioinformatics, but also when you're looking at text, information extraction, translation, all these kinds of things. And so you can try this out right now. We got this into the last release of info.net in the autumn, so you can download it. And it's early days for this feature, so please do give us feedback, and we very much welcome sort of input on where to go with this next. Thanks very much.
Question time.
Yeah. Who's going to zoom in? Or Christian? Christian.
So can you specify more interesting priors over strings? I'm still not quite sure what you mean by string.uniform. Can you sample from that?
Yeah, so you can specify any prior over a string that can be represented by an automata. Now, if your automata has loops in it, it's going to specify an improper distribution. And we've wrestled with that for a long time. Like, do we need to make sure that all our distributions are proper? And it turns out to be a nightmare to try and do that. And actually, it's okay to have improper distributions as long as the result is proper. And so that's what we do. So we allow improper and proper distributions to coexist. So anything that's expressible by an automaton. So the main things that are not easily expressible by an automaton are things like a string that contains these n strings in some order. Right, that's now combinatorially expensive to represent by an automata. But in lots of cases, things are quite compact and efficient. David.
So you said automata are closed under mixture, product, and concatenation.
Yes.
Do you need division to do EP of automata?
That's a good question. You can, with a sleight of hand, get away without doing division, as long as you only care about the structure of the automata. So what you can do is you can take an automaton and say, give me an automaton which is uniform over the support of this automaton. And then you don't need to care about the division, basically. So you can then multiply that in as the inverse method. And then you don't have to divide it out because it was either 0 or constant. And that's the trick that we use. We'd love to be able to divide them, but we can't right now.
Yeah, over there.
How expensive is inference on that? So for your Motif finder,
it's not efficient, particularly at the moment, and that's we've done a certain amount of work on it, and we're using it on an internal system that I can't talk about at large scale. So it's somewhat efficient, but the main problem is that you get like this state automata blow up. And so we've done some work on projecting automata that of high complexity down to lower complexity ones, and there's definitely more work to be done there, and I'd be very interested if anyone wanted to work on that problem. That's a really interesting problem. I think there's some really big performance gains out there. It's decently fast for now. It's usably fast if you keep an eye on your automata sizes and so forth.
Do you have any plans to expand to other classes of automata? For example, push-down automata or other more complicated ones?
In choosing the particular class of automata that we did, we originally chose a simpler class, and then various use cases sort of pushed us into this class. I think it's a really interesting area of investigation. I know that this style of automaton has certain limitations. Determinization helps and so forth, but there's a lot of backtracking needed in certain cases that can be very expensive. So I think it's kind of nice. It would be very nice to explore other kinds. Essentially, we're using it as a function that gives you a weight back for a sequence. And so anything that could plug in there that supported the same set of operators but had better efficiency bounds or something like that would be super useful.
Yes.
what was multiplication? What does that mean of automata?
Multiplication of automata is, in the non-probabilistic case, it means finding the automata that accepts all strings accepted by both of these automata, A and B. So it's the intersection. In the probabilistic case, it means you take those two probability distributions and you multiply them together. In other words, you want to get a distribution out such that the probability of any sequence under that distribution is proportional to the product of the probabilities under the two input distributions.
Great, let's thank the speaker again.
Thank you.